Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we will discuss another topic. Today's topic is the electric field. We represent electric field by E letter. So, in the last lecture, we discussed that the interaction between two charges is studied or discussed under two notions when I have two charges Q1 and Q2. One idea is called action at a distance, in which we say the interaction between Q1 and Q2 is direct and instantaneous. Then we discuss there is an issue with this idea. Issue is its clash with the special theory of relativity, which says that the speed of light c in vacuum is the speed limit of the universe. So we discard this idea and introduce the idea of field. In field idea, we say there is a third party between Q1 and Q2 in the interaction. That third party is field. The interaction is neither direct nor instantaneous. And we said in field idea that Q1 has its own field surrounding it, and in that field, if Q2 finds itself, that field will exert force on Q2. Similarly, Q2 will have field surrounding it, and in that field, if Q1 finds itself, that field will exert force on Q1. And interaction is not instantaneous. If you move Q1, Q2 will sense its movement because there will be variations in the field of Q1. Those variations will reach Q2 not instantaneously but at the speed of light. So now every charge distribution has electric field surrounding it. Now, how we define that? For example, let there be some space. Let me write it clearly. There is some space, and in that space, there are certain charges. There can be many. Let me show two, three charges Q1, Q2, Q3. So there is electric field in the space due to these charges. Now these charges we have shown in the form of points. They can be in continuous distribution also. But whatever the situation, whenever there are charges in the space surrounding them, there is an electric field. Now at this point P, we want to find the electric field. So the question is, what is the electric field at point P? How we find that? What is the procedure? What we do in our procedure, we take a test charge that we denote. Q naught is the notation for test charge. What is a test charge? Test charge by definition is a small positive charge. So whenever it is said that it is a test charge, it by definition or convention is a positive charge and its value is small. Now Q1, Q2, Q3 are the sources of the electric field at point P. So they are sometimes called source charges. Now we are interested in finding the electric field at point P. So what we do, we take test charge Q naught and place it at this very point P. Now at when we place this test at point Q naught, so when we place this test charge Q naught at point P, this test charge will experience force. So let F be that force. So what is F? F is the force experienced by Q naught at point P. So we take a test charge Q naught, place at point P, it experiences force. Why it experiences force? Because there are charges in the neighborhood. It will experience force due to them. So if F is the force experienced by test charge Q naught at point P, then the electric field, let E be the electric field at point P. By definition, the electric field at point P is the force experienced by the test charge at point P divided by the test charge. This is the definition. So you can see electric field at point P will not contain Q naught in its expression because F will contain Q naught. In Coulomb's law, you know, if we have two charges Q1, Q2 separated by distance r, then the force between them is 1 by 4 pi epsilon naught Q1, Q2 by r square. So when you find force between Q naught and the source charges, that will contain Q naught. When you divide by the Q naught, the resulting expression, which is electric field, will not contain Q naught. So electric field at point P is independent of the test charge. So it is one thing about this. It is independent of Q naught. It depends only on source charges. It will contain only source charges. Right? Second thing, it is a vector. It is a vector. How? You can write this as 1 by Q naught times F this way. So 1 by Q naught is a scalar. In fact, it is a positive scalar. So it is a positive scalar. You know from the properties of vectors, if you multiply a vector by a positive scalar, resultant quantity is the vector in the same direction as that of the vector. That means if I have, for example, vector A, I multiply it by 3. 3A is a vector in the same direction as that of A. Of course, its magnitude will be 3 times as that of A. So E is a vector same in the direction as that of F. So it's a vector in the direction of F. Electric field is a vector at a point in the direction of F. But F is the force experienced by a test charge. So whenever you are interested in finding the direction of electric field at a point, you have to think that if I take test charge to that point, what is the direction of the force experienced by it? That is the direction of the electric field at that, right? So electric field at a point is independent of the test charge. It depends only, let me name it equation 1. It depends only on source charges. It is independent of the test charge. It's a vector in the direction of F, right? What about its SI unit? Its SI unit will be Newton per Coulomb. Newton is the SI unit of F and Coulomb is the SI unit of charge. So Newton per Coulomb is the SI unit of electric field, right? Now, another thing which you need to remember is when I take test charge to point P, it can affect the distribution of source charges. So, first understand it. If you change the distribution of the source charge, electric field at point P will change. You can have same charge, but if you change this distribution, the electric field in the neighboring space or surrounding space will change. So, electric field in the space does not only depend on the amount of the charge, source charge, it also depends on its distribution. So when I take this test charge to point P in order to find the electric field due to some given charge distribution, I have to ensure that taking test charge to point P should not affect the distribution of source charge. Therefore, this test charge is taken as a small quantity so that when you take it to point P, it doesn't affect the distribution of source charge, right? So this equation 1 is more precisely written this way, where electric field is equal to F by Q naught, but we write here limit Q naught tending to 0. Simply means that your test charge should be very small, approaching to 0. Why so? I explained to you that distribution of the source charge should not get affected by the test charge. So test charge is to be taken small, approaching to 0, in order to find the electric field at a point. So sometimes you write equation 1 for the definition of electric field at a point. Sometimes you write it more precisely this way, indicating that the test charge is to be taken very small. Now there is another idea related to electric field, that is the superposition principle. Superposition principle. What is superposition principle? Suppose I have many charges Q1, Q2, Q3, Q4. There can be n charges. Now I select some point P and I'm interested in finding the electric field at point P. Now I have many point charges. Now what should I do? Superposition principle says to do it, what you do, you find first E1. What is E1? Electric field at P due to Q1 alone. That means you find electric field at point P due to just Q1 using that definition given by equation 1 or 2. You take test charge, find the force, then divide that test force by the test charge, you get the field due to Q1. And when you find E1, that is field due to Q1 at point P, you assume that other charges are absent. They are not there, right? Similarly, you find electric field due to Q2 at point P due to Q2, then you find electric field due to Q3 at point uh, P, and in these situations you assume other charges are absent. So when you find E1, you assume 2, 3, 4 up to Qn are absent. When you find E2, you assume just Q2 is present, rest of the charges are absent. Then you find E3, assume Q3 is present, other charges are absent, and do the same procedure for all n charges. Then if E is the net electric field at point P. To get that net electric field, what you do, you vectorially add these individual vectors E1, E2, E3 up to En. This idea is called principle of superposition. Let me name it equation 3. This equation 3 can be written in compact form. I can write E, that is the net electric field at point P, is the summation EI, where I is I runs from 1 to n. This summation sign means we have to add first E1 with E2, then E3, and so on. So this is how we get the net electric field at point P. This idea is called principle of superposition. If you state it, you say that electric field at a point P due to some charge is independent of the presence or absence of other charges. By that I mean whether Q2, Q3 or Qn up to Qn are present or absent, that doesn't affect the electric field at point P due to Q1. This is the meaning of it. Because when you find the net field, you find these individual fields E1, E2, E3. In calculating these individual fields, you assume other charges are not there because that their presence or absence is not affecting the electric field, right? So this is how we use superposition principle to find electric field due to many charges. So if you have a single charge, you do use E is F by Q, Q naught, or if there are many charges, many point charges, what you do, you use the principle of superposition, right? So this is how we use principle of superposition. I hope it is clear to you. Now I will do a simple problem. I have secured this page. I will use this. So let me write the question. It's a simple question. Two charges, one of plus 5 into 10 raised power minus 7 coulomb, and the other of minus 2 into 10 raised power minus 7 coulomb attract each other with a force of 100 Newton. How far apart are they? It's a simple question. There are two charges. One is plus 5 into 10 raised to the minus 7 coulomb. Other is minus 2 into 10 raised to the minus 7 coulomb. They attract each other obviously because they are unlike charges. Now they attract each other with a force of 100 Newton. We have to find R. There is simple solution to it. From coulombs now you know the magnitude of the force is K Q1 Q2 by R square. So we're interested in R. So when you solve for R, R is square root of K Q1 Q2 by F E Q1 Q2 by F square root. So let us put the numbers. E is 9 into 10 raised power 9 in SI system, that is Newton meter square per coulomb square. This is my K. 9 into 10 is per 9 Newton meter square per coulomb square. Then I have one charge which is 5 into 10 raised power minus 7 coulomb. Then I have another charge which is 2 into 10 raised power minus 7 coulomb. 2 into 10 raised power minus 7 coulomb. Then I have F in the denominator, which is 100 Newton. I write in the power of 10, 10 is per 2 Newton. So 9 into 10 is per 9 times 5 into 10 is per minus 7 times 2 into 10 is per minus 7 divided by 10 is per 2 Newton. This whole thing is in the square root. So when you solve it, it turns out to be, first when you calculate the numbers, it will turn out to be 9 into 10 raised power minus 6 meter. Meter is outside the root. Let me clear it. So that means it is 3 into 10 raised power minus 3 meter, which can be written as 3 millimeter. So this is our R. This is the distance between these charges. Must check it at home. Check this calculation. Check this calculation at home. So let us move, or I should give you some homework. I will give you homework. This was my page 1. This is my page. Where is the page next? Okay. I've secured many pages. So let me give you the homework. Question. Two charges repel each other with a force of 10 raised power minus 5 Newton when they are 20 centimeter apart. Part A, what is the force? What is the force on each when they are 5 centimeter apart? Part B, when they are 100 centimeter apart. This is question 1. Meaning 1, two charges repel each other with a force of 10 to the minus 5 Newton when they are 20 centimeter apart? What is the force on each when they are 5 centimeter apart? Partly when they are 100 centimeter apart. Then I will give you another question. Let me use another color. Question 2. Under what circumstances, if any, is the gravitational attraction between two protons equal to their electric repulsion? This is second question. Under what circumstances, if any, is the gravitational attraction between two protons equal to their electric repulsion? These two questions is your homework. Do them at home. So this is all for today. Don't forget to like, share, and subscribe my channel. Can you comment in the comment box? Thank you. Assalamu alaikum.